I'd like to welcome all of our guests here for the annual Jansky Lecture. The Karl G. Jansky Lectureship is an honour established by the trustees of Associated Universities, Inc. to recognise outstanding contributions to the advancement of radio astronomy. First awarded in 1966, it is named in honour of the engineer who, in 1932, first detected radio waves from a cosmic source. That was Karl Jansky. His pioneering discovery of radio waves from the central region of the Milky Way galaxy really started our field and led us to here this evening. Unfortunately, there are usually members of the Jansky family here. There aren't any tonight, but David Jansky sends his compliments. NRAO is pleased to award the 2023 Karl G. Jansky Lectureship to Dr. Paul Vanden Bout, who is a Senior Scientist Emeritus and former Director of the National Radio Astronomy Observatory. Dr. Vanden Bout played a crucial role in turning the idea of a millimetre array into reality, culminating in the creation of ALMA, the Atacama Large Millimetre and Submillimetre Array. His leadership was instrumental in forming the International ALMA Partnership and securing funding for the construction of the instrument. While Director of NRAO, his vision and efforts significantly contributed to the radio astronomy landscape, and in fact most of NRAO's amazing instruments today came to fruition during his time. Not just ALMA, but there was also the Very Long Baseline Array, the Green Bank Telescope, and the planning, the initiation of the expanded Very Large Array project. Paul's primary scientific interests lie in using molecular spectroscopy, especially at millimetre wavelengths, to deduce the physical characteristics of star forming interstellar clouds. Recently, he published a new book with co-authors Bob Dickman and Adele Plunkett entitled The ALMA Telescope, The Story of a Science Mega Project, which details the history of the ALMA project from its earliest beginnings to its inauguration and its first decade of science. Tonight, Dr. Vanden Bout will discuss millimetre astronomy at NRAO, some personal remembrances. Please join me in congratulating Paul as our 2023 Jansky Lecturer.
There you go.
David.
We're good?
And there's your fake check.
Oh, thank you. Well, I should thank you, Tony, for that generous introduction, but I'm a little worried that you raised the expectations of the audience. Let's see what I can do. I had no intention of being an astronomer. I didn't have a telescope when I was a kid. I had a average interest in what went on in the sky, but that was about it. I was interested in physics. Went to Berkeley in graduate school in physics, and that building, the physics building, is right next door to astronomy. So I heard occasional talk in astronomy, and particularly I remember one after Sandy Weinreb discovered OH, and Charlie Towns was pleased because OH was a maser. He found masers in the heavens, he invented the maser, etc. After graduate school, the young people may weep to hear this, but you did not apply for a job. Your supervisor called his friends, and you picked the best offer. It was a long time ago, of course, that was 1965. I went to Columbia University to work with Bob Novick, an atomic physicist who had decided to do X-ray astronomy from sounding rockets. And that sounded like a lot of fun, so I went to Columbia. It was not a lot of fun, okay? Novick was impossible. You built a package that went in a sounding rocket. The thing took off, and likely as not, it blew up. My roommate, office mate there, was Roger Angel. And the two of us decided we needed to escape. And we did. We had become acquainted with people at McDonald Observatory, and we ended up at UT Austin in the astronomy department. Roger went on to the University of Arizona to make big mirrors. While I was there, I became a radio astronomer and I'll tell you about that in a minute, a little bit. The first thing I want to do is, let's see, there we go. Radio. What's radio? So it's light. Here's the electromagnetic spectrum. You can see it goes from X-rays, gamma rays, X-rays, ultraviolet, and then this tiny little slice here of visible light, and then the infrared, and then a huge band that's radio astronomy. Now, visible light is important, beyond the fact that we can see it. It's important because it contains tremendous amount of information about atoms. And radio, particularly at shorter wavelengths, tells us about molecules. And that's mainly the story of this talk. So here's the NRAO 36-foot telescope at Kitt Peak. It's in an astrodome. And at Kitt Peak, following the discovery by Charlie Towns of ammonia and water in space, a search was made for a molecule that would transform astronomy. Transformational science, that was a buzzword at NSF for a long time. I don't know if they like to bandy that around today, but it did transform astronomy. So let me explain a little bit about CO, the molecule they found in space. So we want to go back, and here's a crude model of the CO molecule, and any axis perpendicular to this axis, any one you pick, it will tumble around, and it can't tumble at just any old rate. The rates are specified by quantum mechanics. It's either the minimum amount, a little more, double that, and so forth, all the way up. And so when one of these molecules in space bumps into something else, like a hydrogen molecule, which is the most abundant one in interstellar space, it gets excited, it gets kicked up, and then it bumps down. And each time it does that, it sends out a photon. And what Penzias, Jeffords, and Wilson found is they observed this line right here. And here's their spectrum. Now, those frequencies are very well known. 9 places or something like that. And so they tuned their receiver to exactly this frequency, and they saw this huge signal. This is the strength of their signal. And it's spread out a little bit because the CO molecules in Orion are in a gas cloud that's turbulent, and so the motions of the gas spread things out a little bit, but the important thing is they detected it almost immediately. It was powerfully strong. So this makes CO a wonderful molecule to look at. Now, there are other reasons for looking at CO and molecular clouds that we'll get to in a minute. And CO was subsequently detected throughout the Milky Way. I thought they deserved a second Nobel Prize for this, but I assume some observer would have done it shortly after they did it, so they didn't get that. Now, this is a very familiar picture from the Hubble Space Telescope of the so-called towers of creation. Their PR department is first rate. It's in the Eagle Nebula. And what these are clouds of microscopic dust particles that scatter the light from the background stars. So you can't see through these clouds, the same way you can't see through a dust storm. But radar works perfectly all right. You can get a speeding ticket in a dust storm if you're crazy enough to speed. And so millimeter observations see into these clouds. And they can see right into the towers, and that informs the process by which stars form. Astronomers always suspected that stars formed by gravity pulling together material until it got dense enough to condense into a star. But it wasn't possible to see it in the optical because of the dust scattering. But if you can look at the molecules in the cloud, then you can learn about temperatures, densities, motions, the composition of the cloud, and learn a great deal. So I was at UT. I was supposed to be their space guy because I'd done X-ray astronomy. That didn't last very long. Pat Thaddeus and I observed on the 107-inch telescope. We got some time to do some observations, and while we were there wandering around, we went down the hill a little ways, and there was this telescope. It's a beautiful little telescope, 5 meters across, nearly, gold-plated surface, and idle. Nobody was using it. It had been built to look at the planets and measure how bright they were at millimeter wavelengths, and that happened occasionally, but not very often. Pat knew that Penzias wanted a lot of time to look at CO, and Dave Heshin gave him some time. But after the discovery of CO, the 36-foot telescope was so popular that he couldn't give him all the time, and he was looking around for an opportunity, and so Pat and I quickly put together a partnership with Bell Labs receivers. Pat brought some equipment, Harvard brought some equipment, and UT provided the antenna. And the little MWO did really well for a nice run. We had lots of students and visitors. I think 24 PhD theses came out of there, including people that are, it was a while ago, they're now retired from the NRAO staff. Okay, where are we going here? We were not alone. At UMass, they had a 14-meter telescope. Bell Labs built their own. Thaddeus built 2 of these mini telescopes, one at Columbia that went to Harvard, where it still runs, and one on Cerro Tololo in Chile to do the southern sky. Now moved to the observatory there, the National Observatory. And then Aerospace Corp had a 5-meter on the roof of their building right next to the LA airport. Bob Dickman was the manager of that for a number of years. And then abroad, and this was worrisome, the Japanese built a 45-meter telescope, and the German-French-Spanish partnership called IRAM built a 30-meter. So this was worrisome. And NRAO proposed to build a 25-meter telescope then on Mauna Kea. But that project failed. It was due to skyrocketing inflation and Reagan's decision to cancel all federal spending on construction. So the community got together they got together at Bell Labs to try and decide what to do. And they decided they had a better idea than building a big single dish. What the field needed was high angular resolution. And radio astronomers know how to do that. So what do we mean by angular resolution? So we mean the finest detail you can see in the image that's produced of the sky. And it depends on 2 things: the wavelength that you're using in your receiver divided by the diameter of the telescope. But for an interferometer, it's the wavelength divided by the separation of the antennas, and the largest separation sets the ultimate resolution. So we know about these things, right? The Jansky Very Large Array is an example of an interferometer. And this is its smallest configuration, but it has the resolution of a single dish that's this big. I mean, that's enormous. Sadly, most of the signal falls out here in the dirt. But, there's quite a bit of collecting area there, and the VLA is very powerful. How does it produce an image of the sky? Well, that's done with some special electronics and the magic of mathematics that we won't discuss tonight. Here are some typical resolutions. So your eye is good to about 60 arc seconds. And big telescopes on the ground, optical telescopes in the visible, about 1/10 of an arc second. And the Hubble Space Telescope in space, about 1/10 of an arc second. Now, the Green Bank telescope actually works at millimeter wavelengths. We'll see that in a little bit. And at 2.6 millimeters on a windless, cold winter night, you can get a resolution of about 6 arc seconds. So what if you wanted to match 1/10 of an arc second? How big a telescope would you need? Well, it'd be pretty big. It'd be 6 kilometers in diameter. This is not achievable. But with an interferometer, of course, like the VLA, at its highest operating, shortest wavelength, let's say, you get 43 milliarc seconds. And the VLBA, you get 120 microarc seconds. And the Event Horizon Telescope, which is like the VLBA over the whole world, you get 22 microarc seconds. So I only show this to tell you that when it comes to resolution, we radio astronomers have left our optical cousins in the dust, okay? Now somebody might say, wait a minute, there are optical interferometers, and indeed there are. And they can produce a resolution comparable to the VLA, but they're not nearly as flexible or powerful as our radio interferometers. There were pioneering millimeter interferometers. At Hat Creek, Jack Welch, shown here, built a series of interferometers, a series of them that led to the BIMA array, it was called. And the first scientific result from a millimeter interferometer was made with an early 2-antenna version of that. Richard Hills and Jack and others. There was a similar small interferometer at Bordeaux Observatory in France, used to look at the sun. They published their papers back to back. And then in Owens Valley, there was a 5-antenna array, very wonderful antennas that Bob Layton put together. In time, these two were merged together to form Karma, a facility that Tony is well acquainted with since he was the project manager that got Karma going. The earliest versions of these were contemporary with the first concept for a national millimeter array. And that's this. Fraser Owen, a staff scientist, published a memo to the staff in 1982 to build a national millimeter array that looked like this. Now, it looks astonishingly like the VLA, and indeed, it was supposed to have stations along the stations of the VLA, use that infrastructure, 15 10-meter antennas, and then 15 3-meter antennas, which would provide sensitivity to more distributed sources. This is actually a revision of Fraser's first memo. The 3 meters were put on this big platform here that steered around, and then it had certain advantages, even though I didn't think it passed the laugh test. It wasn't clear to me that was feasible. I thought this was a great idea. I was quite enthused. And the MWO and the other small antennas were sort of at the end of their scientific usefulness. And so I was on a bunch of NRAO committees, the users, the visitors. We all saluted this idea, said it was great. And I was asked to be on the search committee for a new director. So we met at the Dallas airport, and we called, I can't tell you how many people, and nobody wanted that job. Okay? And then Bob Hughes, the chair of the committee, said, well, would anybody here be willing to consider it? And Carl Hylas and I, put up our hands a little hesitantly. And so they kicked us out of the room, and they said, we're going to interview on the spot. So Carl went first. And afterwards, I learned that he delivered a 30-minute rant on what was wrong with NRAO. And he came out and collapsed in a chair and looked at me and he said, "You do it." And indeed, they did offer me the job, and I was encouraged to take it by Dave Heeshen, Ken Kellerman, Jay Lockman, others. And so in '85, I went to NRAO, all excited about building the millimeter array. Okay, that was 1985. ALMA was dedicated, put into service in 2013. Okay? What took so long? It's ridiculous. Well, there were distractions. First of all, Kellerman wanted to build a VLBA. Senator Byrd wanted to build the Green Bank telescope. And we all wanted to improve the VLA. All these things took a little while. Here's the VLBA. It's got antennas in Hawaii, St. Croix, scattered around the U.S. Ken Kellerman, the chief protagonist, had an office 50 feet from mine, so I couldn't possibly ignore the project. Besides, it was very high in NSF priorities. But it was a tough project. Peter Napier was the project manager, and he never knew how much money he was going to get and when he would get it. NSF had a really tough time funding it. But that all got resolved in a very curious way. Ron Eakers and others decided that what NRAO really needed was a supercomputer to reduce the data. And indeed, a high-level committee, big shots in the business, had recommended that NRAO get a supercomputer to reduce their data. The only dissenting voice on that committee was Arno Penzias, who said, if you wait a few years, you can buy a supercomputer that will fit in a cigar box. We did not wait, okay? Went charging off to Senator Domenici, who wanted a supercomputer that would service the 3 universities in New Mexico and NRAO, be housed in a building on the Tech campus in Socorro. He called Eric Block, the NSF director, into his office and said, "I want a supercomputer." And Eric is, he's not soft-spoken. He said, "No way. I've got one in San Diego, I've got one in Illinois, I've got one at Cornell, use those." And he was adamant. Now, Domenici had a lot of integrity. He was a big supporter of NSF, and there was no way he was going to bully Eric Block. And I heard about this from a staff member, and she said, when you go in there and he tells you you're not getting your supercomputer, ask him for something. So I asked for the building. I said, we need the building anyway. Even if it doesn't have a supercomputer, we need to run the VLBA somewhere. And he provided the building with New Mexico funds. And Block was so impressed that he saw to it that the astronomy division had regular funding after that. Peter had a regular schedule on which he finished the thing within budget. So it all worked out. Now, this is a 300-foot telescope before. It got a pretty bad review in a big high-level panel, and I think the telescope was pretty much embarrassed, and it just gave up. So that was after. Although we now know that there were incipient cracks in the structure, and that Jim Condon's survey of the sky hastened this to final collapse. After the initial shock, George Salsett called me up at 11 o'clock at night, and he said, guess what? We organized an investigation, and one of the things, one thing and another, trying to handle the media and so forth. But then I thought, gosh, maybe this is the end of Green Bank, right? The 140-foot demand had fallen off. The 300-foot was gone. What's going to happen? Well, George had the same thought. George Seilstadt was a site director. And so George called Senator Byrd's aide and said, we've got a problem. He didn't tell me this because George was deeply suspicious of anything in Charlottesville. He didn't trust me. I was glad he didn't tell me. I mean, he did it on his own. I'm innocent. We went up there around Thanksgiving. The thing collapsed early in the month of November. And there we were, lined up. I was there, George, Eric Block, Bob Hughes from AUI. And on the other side of the table was Senator Byrd and Senator Rockefeller. And Rockefeller did all the talking. And it was the rawest display of power I have ever seen, okay? Rockefeller, he's very tall. He leaned over and looked at Block, who was very short, was sitting next to me, and said, Dr. Block, we want to help you. And Block started dissembling and saying, well, you know, the foundation has its priorities and plans and blah, 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 and he was interrupted. And Rockefeller said, our leader here is going to be chairman of appropriations. And he will have his thumb on every dime in the federal budget. Do you understand what I mean when I say we want to help you? It was very awkward, and Hughes saved the day. He said, we will write a proposal and put it through the NSF process and see how that goes. And Senator Byrd thought that was a good idea. He was so red in the face, I thought he was going to explode, but he did calm down. And so we did write a proposal, and I think it was perhaps the first major construction proposal at NSF that was funded before the proposal was reviewed. Okay. The construction of the telescope was fraught, I think is the word. We didn't want to build any old telescope. I mean, this thing had landed in our lap. So it got an unblocked surface, which has its advantages we don't have to go into, but it's sort of a satellite TV antenna on steroids. And this surface of some 2,000 panels, I think, at the corners, it had actuators that could move. So when you tipped the telescope, you could adjust it and keep a perfect parabola. And so we hoped to make it work at short wavelengths. The difficulty was that the contractor said in the specs that the mechanical part should last 20 years, by which he meant the motors and the gears, and by which we meant the whole thing. And we ended up in arbitration court where our heroes were Randy Squires, our attorney. Dave Hogg was a huge help. Harvey List was fantastic in supporting the arbitration. I think we won in the end partially, Randy said, because Bob Hall, the project manager, had served under Patton in World War II, and the judge was a World War II buff. So if you believe that. In the end, we had offered them $4 million to settle at the outset. At the end, we owed them $7 million and they owed us $3 million, a difference of $4 million, plus the attorneys. I think the Xerox bill came to $150,000. I mean, it was unbelievable. Don't ever go to court. Always settle. It is the world's largest millimeter telescope. Okay, this is the same line that Penzias, Jefferson, Wilson looked at in Orion. It's beautiful. And you can see even the shape. This Luis Rodriguez in a previous Jansky lecture may have mentioned this. This is due to an outflow source that he found. Yeah, it actually works at millimeter wavelengths, which is great. I mean, I wasn't sure it was going to work. People would say, "What if it doesn't work at high frequencies?" I said, "Well, we'll use it for pulsars." You know. So the millimeter array officially began as a project in 1990 when we submitted this proposal. Fraser and Bob Brown, who managed the project, sort of. Bob managed the millimeter array project. I looked for the money. Fraser did a lot of the science that went into it. And it got fabulous reviews. But that was 1990. You know, ALMA, you know, we're waiting on ALMA till 2013. It got a boost in the sales pitch because of this. Bob came into my office, Brown, came into my office and he said, "We have to look at this source." So this long, crazy number, astronomers are terrible about labeling things, but this is something that was seen by the IRAS satellite. It's a faint source, and the preprint that Bob had found said they had identified it with a galaxy that had a redshift of 2.3. That's a long ways away. And he said, "Why don't we look for CO?" Well, CO had been detected, the highest redshift that had been detected was 0.1. So this is a big jump. And we went to Kitt Peak and used the 36-foot to do it. By then, the 12-meter it was. It was in the summer. Observing conditions were terrible. This is the spectrum we got. And the spectroscopists here will recognize this as a truly terrible spectrum. Okay? It's not great. But we believed it because if we looked at the quasar 3C380 with the same setup, we didn't see anything. So we published a paper that said we detected CO at this high redshift and then proceeded to make a totally faulty claim as to what this signified. We claimed it was a massive galaxy in formation. And the reason this detection is important is two reasons. One is, in review committees, everybody, even the optical astronomers, and they're the majority in all the review committees, national review committees, recognize that this enabled radio astronomers to study star formation in the early universe. The other reason it's important is that Dennis Downs at EROM did a proper analysis of the data and concluded that the source had been magnified and increased in intensity gravitationally by an intervening galaxy. And that meant that if you wanted to see an unmagnified population of such galaxies, you needed a huge array. So the Europeans designed a gigantic collecting area for their project. We went to look for a site. We started, of course, in Socorro, the center of the universe for many in Socorro. We looked on Mount Baldy, and then we measured the atmospheric conditions in Arizona, and they were a little better. And then on Mauna Kea, and they were still better. And Bob Dickman said, "You've got to go to Chile." He was our program officer at NSF. And so Brown and I went down to Chile, and we organized this little site search committee. So there's Bob, me. This is Angel Otarola, who is an expert on sighting telescopes. He works for ESO, and he's a desert rat. He knew the Atacama Desert. He knew every oasis. He knew all the people. You know, it's just a fantastic help. And Hernan Quintana, a former NRAO postdoc. And Ricardo Giovanelli took the picture. So this is a site suitable for the millimeter array, or ALMA. It's huge. You can spread the antennas out. It's just like the plains of San Augustine for the VLA, and it's high. And the Smithsonian Institution wanted to put their sub-millimeter array here. But the secretary of the Smithsonian said no, it had to be in U.S. territory, so that never happened. And we decided that the village of Oyahwe was such a sorry place, and at the end of such a terrible road, that we didn't want to go there. And Hernan said, I know a nice place. It's called San Pedro de Atacama. It's a really, you got to see it. I go there on vacation. And Angel knew all about it. And Bob had looked at topo maps and knew that there was some flat land nearby. So Angel tried to explore it. He was stopped. He saw the site. He was stopped from going down because of snow in the road. But he told Bob how to find it. And Bob did find the site and explore it. And this is a shot of a few of the ALMA antennas on the site, which is at 16,400 feet. Now, this site, as you can imagine, presented some problems in building a telescope up there, and problems we didn't actually fully anticipate. Why would we go there? And this is why. This is the transmission to the atmosphere. So this is perfectly transparent, and this is totally opaque as a function of frequency. And these are millimeter wavelengths here, these frequencies. So you can see here's a window. There's another one. Now this is pretty good. And there's a little line here, but this is not bad. And then it gets a little worse. And then there's a bump here and one here. And those are the ALMA receiver bands up at the top, unoriginally numbered 2 through 10. You go there because half the oxygen is gone, which is what causes these lines, and almost all the water is gone. This is for 1/4 millimeter of precipitable water vapor, which is pretty dry, but typical of the best observing conditions on the site. So that's why we went there. There were 3 projects underway: the millimeter array, the large southern array at ESO, and it was large because Down said it had to be large, and the large millimeter, submillimeter array of the National Astronomical Observatory of Japan. And these all merged together into ALMA. The sort of watershed moment was this: the merger of the LSA and the MMA in June of 1997. Ricardo Giacconi, who was Director General at ESO, and I signed this, with no authorization, whatever, this resolution to cooperate. So here are the elements, and this kind of set the tone for the project. It was going to be a big array. So the Europeans got what they wanted. And it was going to go to the high site. So we got what we wanted, because we wanted to do lots of frequencies, and they were mainly concerned with lower frequencies, lower millimeter frequencies. The 50-50 deal between the U.S. and Europe, Ricardo said to me on the phone, he said, we're not going to be less than 50%, And I said, neither will we. So there we were, 50-50, and a promise to bring Japan in. And importantly, ESO and NRAO were to do the job. There would not be a new observatory. This was great because on the basis of this, Neil Lane decided he could give us design and development money for ALMA. I met him for breakfast in Ebbitt's Grill. He liked to go to Ebbitt's Grill early in the morning before he went to work and meet people and talk informally. Somebody was there, and I can't remember who it was, who said, that's all very well, you want to go to Chile, but who's the senator from Chile? And they knew you needed a champion on the Hill, and I said, that's going to be Pete Domenici. And it turned out to be Pete. So this is the partnership. Don't even attempt to read this. This is what it takes to describe what ALMA is. It's the official statement negotiated, I don't know, it must have taken months. A very complex partnership with, I think, 21 countries involved at this point. We had near-death crises. Neil came through We had 3 years of design and development money. It was ready for construction. And then the NSF director, Rita Caldwell, decided to insert her own priority, NEON, the National Ecological Observatory, whatever, network, into the queue. And so, and Bob Dickman heard that she intended to design and develop Alma to death. We thought, this is a disaster. And indeed, we did not appear in the budget that they proposed. And so would the senator from Chile rescue us? And indeed he did. The first thing he did was extend the design and development money by a year. And the next thing he did was put this language in the Senate appropriation. So he gave a bunch of money there to NSF for research equipment. That's the line we were in. And $12.5 million for initial construction. There it is, Rita. You got to do it. So she did. Okay, so that was wonderful. Now, why did Pete do this? How would I put this? We had, you need help on the Hill. And it was all perfectly all right for me to talk to aides and stuff, but Ricardo made a good decision. He decided to get professional help, okay? So he engaged Louis Burke to follow this project on the Hill, keep track of it, make sure we knew what was going on, foster support for the project. But when we talked to him about Alma and the millimeter array, the name came in sort of halfway through all this, he would always turn the conversation to his favorite facility, the VLA, the VLBA. And he knew we wanted to upgrade the VLA. So he provided money to NSF in addition to their budget every year for us to upgrade the VLA. And when that was underway, he was willing to talk about Alma. And I encouraged him. It wasn't too much of a stretch. I told him we would build some Alma parts in Socorro. And then, it all worked out. So I think one of the, my good friend April Burke got the support for LIGO, which you've heard about, and she did the same thing for Alma. So good for you, Ricardo. We had other near-death crises. Our director, Tony Beasley, took over as project manager for Alma and discovered that there was a crisis. Massimo Turinghi had been the project manager. He's from ESO. He had spent all the contingency. There was no contingency left. But they didn't bother Massimo. He was from ESO. They had a guaranteed annual budget. They would just sort of stretch the years out and everything would be lovely. That's not how it works at NSF. So Tony constructed a plausible, a realistic budget, okay? We cut the number of antennas to 50, along with all the electronics that went with those antennas. Taiwan got added as a new partner. We still needed 40%. A big increase. We were worried that the project might get canceled. But Bob Dickman organized 3 very high-level reviews and then sold it to the director and the National Science Board, and they went along with it. So NSF's commitment to big projects, transformational science, and ESOs, they were into big projects, saved the day. And the other crisis was the antennas, the biggest part of the budget. There was a lot of acrimony over buying those antennas. Would they all come from the US? Would they all come from Europe? We ended up splitting them. If you want to know that story, the details will be, I'll tell you where to find it later. Okay, so at a cost of over $1 billion, was Alma worth it? this star, now where am I here? There we go. H. Altauri. It's a young star. It had more infrared emission than a normal star should have, and so it attracted the attention of a number of people. Early, lots of people observed it in the infrared. Anila Sargent and Steve Beckwith did a lot of work on it. And then Kwan, in 2011, looked at it with Karma. And this is the image they got. And sure enough, it's a big disk of heated dust. See, this is their resolution element, this little white circle here, and it's clearly much bigger than the resolution element. And so there it is. But when ALMA looked at it, this is what you got. So this is the ALMA resolution element here, and the whole thing is resolved into these rings. So you still see the dust, the heated dust here, but there are these dark lanes in between. What's going on there? Well, that's where the dust has agglomerated into bigger things, boulders, and is building up protoplanets. So what you're seeing is a solar system in formation. Well, this made a huge impression on everybody that worked on the project. I mean, you could hear the sigh of relief worldwide, and it made a big impression on others. I was asked to serve on a panel, National Academy panel, that was to recommend to NSF how they could improve the ground-based optical observing system in the U.S., which frankly was a mess. It's always been a mess, and as far as I'm concerned, it still is. But the committee came to the conclusion that there wouldn't be a problem if there were more money. You know, the identical conclusion that every advisory committee to the government has made. And then they started complaining about ALMA eating all the money. So I made a spirited defense, and then the director of a major optical observatory said, look, folks, if somebody had showed me this image and said, it's yours for $1 billion, I would have said it's a bargain. And that shut them up. It's not unique. You know, D sharp. Now, the astronomers are fond of acronyms. I can't remember what D sharp stands for right off the top of my head, but these are 20 systems initially detected. Now, hundreds of these have been imaged. All right? Now, these stars are not all that far away in the Milky Way. I mean, they're sort of in the neighborhood. When you consider how big the Milky Way is, there's got to be thousands, maybe millions of these things. It's incredible. And we knew of only one not that long ago. Let's see, why is it this? Oh, there we go. This is another thing that ALMA can do. This is an artist's impression. Here's the star, the young star. Here's the position of a Jupiter-sized protoplanet. And ALMA imaged the gas near the protoplanet, and they found lines of carbon monoxide, sulfur monoxide, silicon monosulfide, SiS. And so the significance of this is that you can look with ALMA in the neighborhood of places where there are thought to be protostars and confirm that, in fact, they're there if you see these molecules. You can do astrochemistry. So this, of course, is an optical image of the galaxy NGC 253, but if you take a spectrum of the nucleus, you see spread along in frequency here what looks like noise, but it isn't noise. Every one of these little spikes is emission from a molecule, you know, acetic acid, etc. It's incredible. There are hundreds of molecules now that are known in the interstellar medium. Thaddeus used to call it a kind of cosmic pharmacopoeia or so, ignoring the fact that they're all toxic. So I think it would be quite. The astrochemists are quite fond of telling us that some of these molecules will be the precursors to life. Which is kind of ironic given the fact that they're all poisons. But anyway, this is another big ALMA project, FANGS, which I think is physics at high angular resolution or something like that. And so what you see here is heated dust and very detailed maps of galaxies that aren't terribly far away, okay? And they tell us a lot about galactic structure. You can look at high redshift galaxies. And Aspects is a big project that does that. This is the Hubble image. It's the Hubble Ultra Deep Field. And every tiny little blob here, everything you see is a galaxy. And most of them are at very high redshift. Now, if you look with the Spitzer satellite or with Herschel, what you see, this is Spitzer, this sort of big blob here. This is the Herschel, found this source. All the little contours here are what ALMA sees. ALMA can see all this stuff here. I remember when we wrote the MMA proposal, Bob Brown noted that the MMA, even in its small size, would be very sensitive to these sorts of galaxies. There might be so many we would get confused. They would be on top of each other. Well, fortunately, that doesn't seem to be the case, but it's very, very useful. I think Aspects has had hundreds and hundreds of papers published now, lots of citations. So, in fact, the H.L. Tall paper has been cited over 1,000 times. You can image a black hole. Now, that's the Event Horizon Telescope, which includes Arizona, the 25-meter or the 30-meter in Spain, the SMA and JCMT in Hawaii, the big telescope in Mexico, and Apex in ALMA, significantly, and the South Pole Telescope. These dotted lines to the South Pole Telescope mean they're going to add that at some point, and they're going to add one in Greenland, too. But this is the image they got of the black hole in M87, the emission surrounding the black hole shadowed by the black hole itself. It's an impressive image, but what we're proud of is that this is what you get with the full EHT, and if you don't include ALMA, that's what you get. So ALMA is incredibly important to this very significant project. So I said, if you wanted to know the details, what you've got is the executive summary. If you want to know the details, consult Mark Gordon's excellent book on the history of the 36-foot telescope, which kicked off millimeter astronomy at NRAO, and Kellerman, Boughton, and Brandt's book, Open Skies, which is the history of NRAO, period. There are lots of details there. And now, to set a precedent, the first Jansky lecture with a commercial, you can consult this book. Significantly, you can get it free if you go to cambridge.org and download it to your laptop, or you can buy it at Barnes & Noble or Amazon. So in conclusion, I have to add this. NRAO is the premier radio observatory on the planet. I mean, it's tops. And that's got everything to do with the people that make up the staff. And it's really been a pleasure, a privilege, an honor to be part of the team. Thank you.
Thank you, Paul. Questions? If you have a question, just pop your hand up and someone will come with the microphone.
No question. That's good.
Thanks, Paul. That was a great talk. So you told us all the things that went right? Looking back, if you had one decision that you got to redo, do a do-over on, what would that be?
In my time at NRAO?
Your time at NRAO.
Yeah, I think the worst thing I did at NRAO was get the APES++ project going. Okay? I had ignored Dave Hession's advice. You know, when I showed up, Dave said, be careful of the computer people. He said, I never understood anything they told me. And I got sold on APES++.
Jeff is in charge of the computer people.
I got sold on APES++, and it wasn't a good thing. And I think the best decision Fred Lowe made when he took over was to get rid of the project. Now, I understand there's some legacy in CASA, and I'm pleased that, you know, it led to something. But that's I would have done that over.
Thank you. Next question.
Other questions?
Okay, good. Oh, there's somebody. There's Chris.
Hey, Paul. Great talk. Thanks. I'm just curious what you know about the history of Charlottesville being where the headquarters is located. Well, how was that decision made? Was that an early on decision?
To make Charlottesville...
Why is Charlottesville headquarters? Yeah.
Oh, well, you know, that predates me by a lot. But you could read Kellerman's book, okay? I believe that the scientific staff felt that it was too remote. They wanted to be closer to a university, and so the thought was to move somewhere close to a major university. Robbie was on the board of trustees and wanted them to go to Princeton. But Dave thought that was too far from Green Bank. We ought to be not so far away, and Charlottesville was a better choice. And my understanding is that Robbie did not speak to Hession after that.
Thank you for the talk. It's very enjoyable. Could you talk a little bit about when you first started to plan ALMA? What kind of thoughts did you have, and did you have much confidence that the technology would be ready when the project kicked off?
Sure. The specs we had for the antenna, it was going to be the biggest, most precise antenna that ever been built. Okay, the electronics, the receivers were going to be quantum limited, if we could possibly do that, and it had to be a big correlator. So we got prototypes for the antenna, and they all met specs. Okay, they were tested, European, Alcatel produced one, Radiation Systems, Vertex eventually, and the Japanese Mitsubishi, and they all met specs. So that was amazing. I mean, you know, it's a fabulous antenna. The receivers, Massimo Terenghi I was the interim ALMA director, and he was the project manager at the beginning, and the two of us traveled around to various labs that could make receivers, including the lab here, one in the Netherlands, one at IRAM. We went to Spain, we went to Sweden. And Massimo laid out these specs. And I remember Tony Kerr telling us that it would probably take them 10 years to achieve this level, and they would need God knows how many $1 million to do it. And Massimo, and we got the same story at IRAM in the Netherlands, and Massimo said, you know, well, okay, forget it. We'll just buy them from Japan. But, of course, they did it. And they did it in much less time to fabulous specs within a reasonable cost. I mean, we did have cost overruns on electronics. The big cost overrun was on the site and on the management of the project. I mean, the management of the project was complicated, as you can imagine, and so decisions were delayed and purchase orders were placed, and you know, Tony gave us a whole list of lessons learned, which are in the back of this book. It worked out. I mean, the engineers were a little afraid of it at first, but they plunged in and did a fantastic job. What else can I tell you?
So I'm wondering, you've sort of had a variety of roles over your career, more on the science side and more on the administrative side. What do you think is the skill that you've either used or developed that was the most important or helpful during your career?
What was that?
Between science and administration, what's the most important skill you've developed? What was most important?
Oh, well, for building the array, you need management. You need really good management. People that pay attention to schedule, people that pay attention to so-called human resources. Okay, you have to have a team with high morale because it's a tough job, and it goes on and on and on if you've got 54 or 64 antennas. For designing the array, you need science. I mean, you need people with vision that know what you want to do. NRAO was good at that, and so were the other partners. I mean, they'd all done cutting-edge science in millimeter astronomy. So I would say initially, you need a very strong cadre of scientists who tell you what it is you want to do. That leads to the specs. That leads to management and building the thing. And then the scientists have to keep track while you're building it. You need a project scientist to make sure nobody cuts corners and cuts out a capability when you weren't looking. So you need both. Oh, Scott.
Yeah, Paul, that was great. Thank you very much. So I want to look forward a bit. So ALMA was $1 billion project, okay? Incredibly complicated management, took 30 years or 25 years, whatever it was to do. Do you think that we as humanity, especially internationally, have the stomach or the ability to do a 10 times bigger ground-based project or even 100 times bigger ground-based project in the future? Can we do that?
Well, I think NRAO is attempting to do something much bigger than ALMA, called the New Generation VLA. I think that's possible. NSF has gotten used to big projects, okay? And someday, when they get over this idea that they should do applied research, they may be able to kick in some money for the NGVLA, and I think Tony has ideas for others that might be willing to contribute. I think that project is feasible. And I think we can probably do it, with some good friends. Canada, Mexico, people that we have worked with before. I don't think we will ever do a project when we're a minority partner. ESO will never do another project where they're a minority partner. And so 100 times bigger? I don't know. Good luck.
David, straight up. Yeah.
Well, talking about future, what will be the future for ALMA? I have learned that there are some upgrades planned for that.
There are certainly plans for upgrading ALMA. I mean, I think there's this wide band sensitivity project, a new correlator, better receivers, that sort of thing. The issue is whether the partners will have the money to fund it. By the way, the agreement to operate ALMA expires in, is it 35? Something like that. It's it's 12 years away, but I mean, time flies. Will they sign up, for another 20 years? That's an interesting question. I think they will, provided things like the wideband upgrade and other projects like that keep Alma at the cutting edge, then you wouldn't want to abandon it. If those things don't happen and Alma becomes somewhat dated, I think it's an open question as to whether they'd sign up again.
Thank you very much for the talk.
Questions? Okay, if not, why don't we thank Paul and thank you all for coming.